Upside-down reinforcement learning is a new approach to reinforcement learning where instead of trying to predict rewards from states like value functions in Q-learning, the agents directly predict actions based on the state and then a command. This command consists of the desired return and desired horizon. So say in a given episode, the maximum reward possible is something like plus 10. Instead, the agent might seek to attempt plus 5 in 3 time steps compared to just trying to maximize the reward, kind of relating upside-down RL with algorithms like quality diversity algorithms and intrinsic motivation. Upside-down reinforcement learning is also very interesting in the way that it uses supervised learning to train this behavior function. This video will explain this algorithm and the results reported from applying upside-down RL to Lunar Landing and Doom. This image shows the differences in the mapping functions between upside-down reinforcement learning and then value function-based methods like Q-learning. So in Q-learning, what you do is you take in the state and the action and you map it to a value estimate. So you try to learn the value estimates of different state action pairs to navigate the environment by looking at all the next possible state action pairs and selecting the one with the highest value estimate. But rather than upside-down reinforcement learning, what you do is you map directly from the state with the target reward and the target horizon that you're trying to achieve, and then you go directly to the action in this sense. So in this way, it's more of a policy-based method compared to something like a value function algorithm. This Markov reward process diagram further shows the idea of having this command that is separated between the target reward and the target horizon. So say you start from state S0 and you're trying to get a return of 2 in 1 time step. What you do is you take action A1 to get to S1 and receive that reward. But then you can see all the different ways that you can combinatorially have a return and horizon. So say you want 1 in 2 time steps. The way that you would do that is you would go from S0 to S1 and then you take this -1 reward to get to S3. So you can see how having different desired returns and different desired horizons might cause the agent to more thoroughly explore the search space and find more interesting things along the way. One of the most interesting characteristics of upside-down reinforcement learning is the way that it's able to use supervised learning to train its behavior function, which we'll illustrate further in the next example with some more Markov reward processes. So the idea here is that you define a loss on the behavior function's mapping from the initial state, desired reward, and the desired horizon with the actions that you experience when you're sampling from the environment. So this sampling from the environment is agnostic to model-free or model-based. Just this is the general framework for updating the behavior function using supervised learning. We use this Markov reward process in order to get a better understanding of how supervised learning is used to learn from the experience of the environment and update the behavior function. I've chosen this Markov reward process because it has a longer episode length in different sequences, and also I just think better describes this idea rather than the more simple one described in the paper. So if we're in this Markov reward process and we take this path from S0 to S2 to S4 and then to the terminal state S5, we receive these different kinds of pairs in our replay buffer that we can use to update our behavior function. So you see, if you're starting from state 0 and you want to achieve 2 reward, the sum of 1 plus 2 plus -1 in 3 time steps, you have this exact supervised sample, and the answer to that would be to take A2 in state S0 compared to taking A1. So then in this one sample of experience, we get a lot of different learning, some like targets like labeled data to learn this behavior function from. So from this one trajectory by sampling from the environment, we can then learn from S2. If we want to achieve 1 reward in 2 time steps, which is 2 plus -1, we have this decision that take this labeled example of take A5 rather than say A6. And then also we end with, even though there's only one action here, you can imagine a more complex framework where you have more decisions and you have another labeled example coming from the end of this trajectory as well. Again, just to try to make this example more clear, we can sample another trajectory going from S0 to S2 to S3 and then to the terminal state S6. So the first labeled example we have is if you start in S0 and then want to achieve a reward of 5, 1 plus -1 plus 5, and then you want to do it in 3 time steps, you have this labeled example of A2. So make the decision A2 if you want to achieve this command of 5 reward in 3 time steps. And then we have this next labeled sample where we start in S2 and want to achieve 4 reward in 2 time steps, and the answer to that is A4 compared to A5 or A6. And then we also have the final labeled example of S3, 5, 1, A8. So we see how we're learning this behavior function by having all of these supervised learning examples from sampling from the environment. Putting this together, we have the full upside-down reinforcement learning algorithm. So you can kind of relate this idea to generalized policy iteration as in algorithms like Q-learning and these value function-based methods that learn the value function and then they use this to improve the policy. But in this case, all we have is a policy, but we need to use that policy in order to go and gather more data to do more evaluation. So we have this kind of an exploration loop with respect to our current behavior function and then sort of the experience we want to go and get in order to update it. So the idea here is you first initialize the replay buffer, which we're going to use to sample from and do supervised learning on the behavior function with a random policy. So then what you do is you basically update the behavior function by training on the replay buffer that starts off from a random action, and then you're going to sample the commands, and then you're going to sort of update the experience, and then train the behavior function in this kind of a loop. So the way that you're going to generate an episode using the behavior function is you're going to compute the probability of an action given the state and the command, and then you're going to execute that action, and then you're going to record into the replay buffer the state, action, and reward tuple. Then you're going to increment the state, decrease the reward that you're trying to achieve, and then decrease the horizon, and then repeat this to sample an episode. The upside-down reinforcement learning algorithm comes with a few hyperparameters summarized in this table in their paper. The first is the batch size used for doing the supervised learning of the behavior function, then the scaling factor for the horizon input, the number of episodes from the end of the replay buffer to do that exploration in the environment, which is something we'll look at more in the next slide, and then the learning rate for the supervised learning optimizer, the number of exploratory episodes done in this training loop, the number of updates done in the training loop as well, and the number of warm-up episodes where you're doing this random policy to sort of get the initial replay buffer started to train the behavior function. And then you have the maximum size of the replay buffer, and then the scaling factor. I think this is supposed to be of the return input as well. Like many other reinforcement learning problems, upside-down reinforcement learning has to trade off exploration and exploitation. So the way that they do this is that they sort the replay buffer according to the highest returns that they've seen so far. And then they sample the horizon that is the part of the command input based on the mean of the lengths of the episodes. So say the highest returns are sorted, and then the horizon that it took the time steps to achieve them are say 8 time steps, 6, and 4. You would then set the new exploration horizon to be 6. Then you're sampling the returns that it's looking to achieve by taking from the uniform distribution of the mean of these top replay buffers and then adding the standard deviation from this mean. So say it's like 8, 7, 6. You're going to have this kind of adding 1 to the mean of it. So it'd be trying to get 8 or 7 in that case. So there's many other ways that they describe of doing exploration in a different paper that is on the same topic but written just by the Jürgen Schmidhuber is reinforced learning upside down, don't predict rewards, just map them to actions. In the paper, the authors experiment with 2 OpenAI GYM reinforced learning problems. Lunar Lander, where you have an 8-dimensional vector input, and you're trying to land this rocket ship on the ground by controlling the main and side engines. And then Doom, where you have this 32 by 32 grayscale image, but what they do to make it Markovian, because you can't always see the walls, is they stack the 8 most recent 32 by 32 frames together to make it like an 160 by 160 input. And they also have an embedding for the reward and the horizon that combines with the state representation to form the behavior function mapping from state and then the target reward and horizon to the action to take. These plots show the results of applying upside-down reinforcement learning, an actor-critic algorithm, and deep Q learning on Lunar Landing and the Doom task. So on Doom, upside-down reinforcement learning outperforms the other algorithms, and then on Lunar Landing, it underperforms. On the Lunar Landing task, the authors note that they can restructure the reward function. So instead of being a dense reward where you receive, say, +1 or -1 for every time step, and then have this kind of +100 or -100 when you're getting close to a certain area near the landing, if you instead have it as be a sparse reward and you only get rewarded at the end of the episode, they actually find that upside-down reinforcement learning does outperform the actor-critic algorithm and the deep Q learning algorithm. This plot shows the gains by having a sparse reward function rather than the dense reward and having the upside-down reinforcement learning algorithm outperforming deep Q learning and actor-critic algorithms in this case. So I think it's really interesting to think of the way that the reward function is designed and how it might limit different paradigms for reinforcement learning like upside-down reinforcement learning. These plots further show how well the upside-down reinforcement learning agents are able to do the mapping from the desired return with respect to the actual return. So for example, they're not always trying to maximize their return, rather they might try to target a -100 reward or say an intermediate value like 100. So in this plot, it's able to pretty much achieve the reward that it seeks out to achieve, and it does an even better example of this in the sparse reward case, but then it also shows in plot C how sort of different agents they generalize differently. So this agent, same kind of idea, just a different training seed, does a good job of aligning the target reward with what it actually achieves compared to this plot. And this plot also shows the results of this on the Doom task. I think upside-down reinforcement learning is a really interesting framework in the context of things like quality, diversity, and intrinsically motivated agents, where the idea isn't just to maximize reward, but rather to explore the space and try to find something unique. So it's sort of interesting how it's doing this return and then horizon, sort of allowing it to explore the policy in a novel way. For learning more about upside-down reinforcement learning, I highly recommend this video from Yannick Hilcher on YouTube. Thanks for watching this explanation of upside-down reinforcement learning, which is a really interesting way of structuring the mapping function from states to actions in reinforcement learning problems. Thanks for watching, and please subscribe to Henry AI Labs for more deep learning and AI videos.